Good afternoon, everybody. So there's still a few of you coming in. There are plenty of seats down the front here, so please feel free. We'll have a nice, cozy conversation today. So my name is Craig Box. That's my Twitter handle up there, @CraigBox. If anyone's live tweeting along, I'd love your thoughts and comments and questions as we talk today about what's new in Kubernetes and in Google Container Engine. Now, I'm sure a few of you are users of Kubernetes today, but there'll be some here who aren't so familiar. So I'd like to start with a quick recap. What do you think the most common cause of outages is in a business? You think it's bad software? It actually turns out that it's misconfigured software, especially the bad kind of outages where sort of everything goes down at once. So there's a lot of questions that you might hear. You might either ask yourself as a manager, or you may have as a technician, your management sort of ask you. Say, are you scared to make changes in an application that you're running because you're worried that something might break? How many different ways do we have to deploy code to go to production? This is a problem that Ticketmaster have estimated was annually a $60 to $90 million cost to their business. Just moving software around, not building the software, but figuring out how to package it and deploy it to their users. I can't deliver a product because I'm waiting on someone else. I have everything built in a monolithic environment. I'm not separated from people. Why can't we move as quickly as a competitor? Why don't we have that competitive advantage? How many of our deployments fail and we have to roll back? That's part of that multi-million-dollar problem is, well, we need to know that we can safely roll a deployment back to have the confidence to be able to continually roll them forward. And finally, we're paying so much money for expensive servers, but we're only using a single-digit percentage of their capacity. Why is that, and what can we do to improve it? And Google's answer to that is Kubernetes. It's been just under 3 years since we announced Kubernetes, and 2 years since we went version 1.0. It's something that was developed internally at Google and then given to the community. We set up a foundation with the Linux Foundation called the Cloud Native Compute Foundation to steward Kubernetes and similar technologies and make them available to everybody. Over that time, we've seen adoption of these concepts in platforms that build on top of Kubernetes and in other similar platforms who have taken a lot of these ideas. And it's been fantastic to see the learnings that we have from our 12 years of operating container infrastructure at Google out there in the world. So what is Kubernetes? One of my colleagues describes it like this. It's container-centric infrastructure for deploying and managing applications. Okay, well, let's unpack that. What does that mean? First of all, we say, what is a container? Well, a container is two things. It's an application bundle. It's a way of describing how an application runs with all of the dependencies that it needs to run just on a kernel without having to worry about what's installed on the machine next to it. But then it's also a way of restricting what that particular application can do when it runs on that machine. So a great analogy, if you're not familiar with containers, is to think about the modern smartphone and applications that run on it. Booting your phone from cold is like starting an operating system or starting a VM. It's exactly that. It takes around about 60 seconds to boot your application from cold. And the data on your phone is, the data in a virtual machine is mixed in with the image. You download the image, you run it on a machine, and then you generally make changes to the image that if you were to boot that a second time, those changes would still be there. Contrast that with a modern application container that is starting a process. It is like starting an application on your phone, so it happens much quicker. It happens imperceptibly in most cases, so the order of about 200 milliseconds. And you download this as a signed bundle from your app store. You know it will run on whatever type of phone you have. And it doesn't write changes, it doesn't write the data that you generate using the application to that image. That image is kept there, and that data is written off somewhere else, so that when you restart, you can get back into a known good state. Containers have recently been popularized by Docker. There are, of course, other implementations of this idea, which run on Linux servers, and now also Microsoft have Windows containers, so you can run the same concepts on the Windows stack. Now, we want to run applications that serve 1 billion users. We want to do this by sharing across a sea of machines running these application containers. But now we have this distributed resource. We think, well, what are the new challenges here? How do we make sure that the services we run are isolated from each other and they aren't impacted by other workloads that happen to run on the same server as your particular application container? When we're talking now about single machines, it's easy to say, well, I know how I'm going to upgrade or manage this. But if we're going to run a workload across hundreds or maybe thousands of machines, that's another challenge we have to worry about. How do we deal with qualities of service? How do we deal with monitoring, recovering containers when they fail, recovering deployments when they fail, dealing with demand which is not fixed, being able to add and remove containers to scale, dealing with service discovery. So if you want a microservice architecture of even a sort of a traditional end-tier architecture, we have a front end. The back ends now could end up running on any node in our cluster, so we need a service discovery mechanism so that these services can find where the application is running. So running containerized applications at scale changes the patterns of how you want to operate, and that's what Kubernetes is. It is an answer to all of these questions, and it's a path to natively running applications either in a public cloud or in a cloud-native fashion in the traditional data center environment. Now we have a quick piece of audience participation. So first of all, I'd just like every single person to raise their hand. Every single person? All right, so there we are. No one minds if you do it. I have 4 groups here, and I'm going to go through them one at a time, so if you can put your hands down. But I will ask people just to sort of give me a feeling for why people are here today. So first of all, can we have all the developers put their hands up? So I'd say that's a good 40, 50%. And for you, think of Kubernetes as a simple, fast, and fully managed way to run containerized applications from test to production. There's a quote here from the DevOps engineer at a company called Porch, who run on our container engine product. They say, Kubernetes, the ease of deployment accelerates everything for their development teams. You go from commit to deploy in production in less than 10 minutes, and being able to do that allows you to deploy 30 to 50 times a day. Having this automatable infrastructure, having these sealed, hermetically sealed container environments gives you the trust to move quicker, and to do this without needing to bug your operations people. So where are the operations people in the audience? Few, smaller number. For you, think of Kubernetes as a standardized platform for reliable and scalable application clusters without operational overhead. We want to separate for you the thing that you run and operate. You can specialize in running these clusters, and then you just provide a nice contract API to your development groups. They develop against that, they deploy their applications, and then you don't need to worry about what happens to be running. You just give them the tools to do this in a very self-service fashion, and that accelerates the specialism in both of those areas. So we have technical leaders as CTOs. Again, a few of you. So this particular fact applies to both of you, is that the acceleration behind the pattern, again, before Kubernetes, but using containers and the same principles in our internal cluster management system, allowed us to grow the fleet of machines we were responsible for 10x faster than we grew the number of humans. Which leads to the pitch to CTOs, which is that I see Kubernetes as the industry-leading open source infrastructure platform, enabling interoperability, removing vendor lock-in, and providing cost savings. So let's look at the vendor lock-in situation. Here at Google, we have the luxury of a reasonably consistent environment for all our developers to use. But we know that as much as we would love you to bring all of your code and all your applications to run in our public cloud, not all applications are going to be rewritten from scratch, and not all of them are going to run in the public cloud. The reality is that some services will be containerized and some won't. And production environments are even more complex than div and test environments. So what you need is a management stack that can run anywhere that containers can run. It gives you the freedom to deploy on-premise, in a hybrid environment, in a public cloud, in any connection of these, any collection of them. You should make the choice based on the merits of your cloud. Where you want to run work shouldn't be determined by what's provided there. You can make the change based on the business decisions, where's cheapest, where's best to run, where you need to operate worldwide, for example. We want to meet you where you are and support you on this journey. Here's a quote from another one of our customers. It says, Kubernetes did nudge us in the direction of GCP, but they're more cloud agnostic than ever because they know that Kubernetes can live anywhere. We see other vendors now running Kubernetes as a managed service for their customers, and we really want to see this as the API that exists wherever there are machines running you can operate against. So our final group, business leaders, CEOs, anyone in that group? A small number of you, welcome. Kubernetes to you can see it as an access to a vibrant ecosystem and the talent pool to accelerate the rate of innovation and reduce time to market. What does that mean? Well, here are a list of some of the contributors and users of Kubernetes today. Some of those vendors, Microsoft I mentioned before, have a managed Kubernetes service. A number of people who provide infrastructure services like VMware now give you ways to build and easily operate Kubernetes clusters on top of them. We have a bunch of great enterprise customers, as we're based here in the UK. I'd like to call out Sky and Pearson. And Monzo, for example, are running a bank on top of Kubernetes. So it is possible to do great things on this. We've just learned that one of the world's top 10 websites, which is Reddit, is moving to Kubernetes. And we'll be excited to share more about that as it comes along. Now, this slide shows the composition of the Kubernetes community, the open source users. We contributed a lot of code in the 1.0 release. You see there it was about 75% of the code. And we have accelerated both the number of engineers and the amount of contribution made from within Google over the last 3 years. But so has everybody else. The entire tide has risen. The community has got larger. So that in the last releases, you'll see that Google is actually a minority of the contributions to Kubernetes. It's all of the people you saw on the slide before, customers, partners, vendors, users, who are contributing. There was an article in Tech Republic last week that said the Kubernetes community was 5x the size of its nearest competitor. So it's a fantastic amalgam of people who are available to deploy, who know these patterns, who are able to deploy clusters, who are out there to be able to hire. It's really democratizing this cluster community. Kubernetes is something you can run anywhere, but we know that Google has a fantastic infrastructure. It has a world-leading network, and we have 12 years of experience in managing environments like this. So we offer a managed service, which we call Google Container Engine, GKE for short. GKE is a Kubernetes service which we manage and our SRE teams run and monitor for you, and I'll tell you a little bit more about some of the features of that as we move on today. Now, about every 3 months, we release a new version of Kubernetes. 1.6 has just come out, so I want to talk about a few themes of this most recent release. First up, we've increased the maximum cluster size to a massive 5,000 nodes. So I want to put that in context. We also have 64 core VMs, and if you were to run 5,000 of them in a cluster, that's 233,600,000 core hours a month, and it'll cost you around about $7 million. And the good news is that here at Google Cloud, we offer continuous use discounts, so you're able to get that cost down to more like $3.5 million. But ultimately, there's not a lot of people who are going to run at that scale. We appreciate that. But what we define is the latency SLO. We say that in order to hit this, we should say 99% of API calls return in less than a second, and 99% of pods, which are units of containers that we run in our cluster, are scheduled and launch within 5 seconds. And now the improvement in this drives down and makes that faster for everybody. So smaller clusters will see great improvements in size using the new etcd3 backend. It's fantastic to know the scales there if you need it, but realistically, you're probably not going to put 5,000 nodes in a cluster. But we want to make it so that you can program your cluster to be the right size for whatever workload, whatever it is that you want to run. Taking principles from our SRE, our site reliability engineering concept, we say, well, what we want to do is build a robot to maintain the infrastructure so I can go to sleep and know that the page is not going to go off. And what we do there is say, we don't want you to care about how many pods you need to run, how much compute capacity you need to dedicate to running a particular service. We want to say, define some criteria. Say, I want to make sure that my responses always return within that particular SLO, or I want to set these minimum and maximum boundaries. So we offer 2 types of autoscaler inside Kubernetes. First of all, we have the horizontal pod autoscaler, which runs inside your cluster. So you dedicate a certain number of machines to be a particular Kubernetes cluster. And then you just say, what the number of replicas you want in your deployment, and the parameters that it will be prepared to scale in between. So I've said that that works with walls. So if you're running an on-premise environment, you have boundaries. You have a room with a certain size, and so you can't scale past that, for example. Or if you do want to auto-scale a new machine, that involves making a phone call to Dell and having someone come out 6 weeks later. So that's why they have a second concept for people running in cloud environments, which is called the cluster autoscaler. What that does is it takes a signal from the horizontal pod autoscaler, which says, I couldn't scale because I ran out of space. My cluster is now full, and then it gives that signal to something which says, all right, I can do something about that. I can provision another node. I can add that to your cluster. I can make it bigger for you. It's fully managed and built into Google Container Engine. There's open source connectors for other cloud environments. And over time, the open source community is working on developing other types of autoscalers as well. Now, I want to take a moment to talk about sizing a cluster. The larger you make a cluster, the more machines you put into it, the more workloads you can fit into that, because you think about it, the chances are there's more chances in empty space that's exactly the same size as the container that you want to run. But inside Google, we don't put all of the machines in a single cluster, because we want to minimize other things. Like, let's say an engineer comes along and says, I want to drain this cluster, and then it turns out that they typed something wrong, which had happened. And you accidentally issue a command and you say, hang on, that cluster's still got traffic coming to it because you accidentally turned off this one. And the fact that you don't see this is what is enabled by these tools and what is enabled by these engineering practices, is that you split up the number of machines you have into these different clusters, and you make sure that when you do upgrades to one, it's not like you have a test cluster and a production cluster, for example. Or worldwide, if you want to operate in different regions, you will have some machines serving traffic in, say, for example, Europe, the US, Asia Pacific. You don't want to have one cluster which spans all of these regions, because if you do, then you don't necessarily have the same latency between machines. So you don't want to say, I'm talking from this to this machine, it's very quick, but talking to this one is 400 milliseconds away. So put them in different clusters. When you do have different clusters, you can connect them together into something called a federation. And this is a way to use a global load balancer to route traffic to whichever cluster is nearest you. And I'm not going to go into that now because we have a session on that tomorrow morning at 11:30 a.m. where my colleague Lionel and I will run through some demos and show you exactly how you can make the most of this. OK, so we've said we've got these large clusters, up to 5,000 nodes. Now, previously, they were all one single security domain. So you'd give someone access to run in this cluster, they'd have access to the entire thing, effectively. What we'd really like to be able to do is dynamically carve it up and say, well, various teams are able to act only on certain amounts of it. And we've introduced in Kubernetes 1.6 role-based access control, which allows you to do just that. So conceptually, think of this as the difference between MS-DOS, everyone here hopefully old enough to remember this, where anyone can read any file that exists on the disk. And then all of a sudden we move to the Unix model, where you have permission mappings, and you can only see the files that are relevant to you. So before we had role-based access control, we had this cluster-level authorization, where again, you had access or you didn't. All of the pods have a similar level of authorization in terms of what they're able to run. Any pod can basically do the same amount of stuff. We did have namespaces. So a namespace is a concept which basically means I can create a pod called web, and you can create a pod called web, but they're in different namespaces, so there's no conflict there. We give a group a different set of things, and then you can run, for example, a deployment which says this is the name of my thing in multiple instances without them conflicting. But you couldn't stop someone in one of these groups accessing the other one. And of course, now you can with role-based access control. We can give those namespaces some teeth. We can say a user exists who's only allowed to do things within that particular namespace, which is a great example when you want to share a cluster between different teams or different groups. So how does that work? It's very simple. As with everything in Kubernetes, it's based around the idea of attaching users or groups, in this case, to resources, which is a namespace. So all users start off with no access. And what we're going to do is we're going to pick a role that we want to use. So there are default roles like a cluster administrator or a reader. And you can create your own. Someone, for example, they can create configurations, but they can't deploy new workloads and new pods. So we take that role, and then we create a role binding using the API, which is going to grant access for that particular user, group, or service account to access those resources with that permission. What does that look like? It looks exactly like this. So here we want to give the blue team cluster administrator rights in the blue namespace. So within their particular area, and we can define a quota on that namespace to say they're allowed a certain amount of CPU or share of the cluster. That particular group, specified here by a group name, bound to that namespace has administration access. So you submit this file to the API server, and then it will create that binding for you. Here's the before and after. So beforehand, you will have a user, you'd say get pods, and it'll say, I can't do that. I don't have permission. We create that binding, and now they do have permission. And if I'd shown you in a different namespace, they'd say you get the same error. They're not able to get pods in the system or the default namespace, but in this group, this namespace we've created, especially for this group, they're able to. So now you can give accounts to each team or to your deployment scripts, your CI servers, and scope them and know that they can't accidentally change things that they shouldn't. And that's very important to being able to say, well, the more work we can pack into these machines, the higher we can make the utilization of them and the lower our cost is. Another feature that's top of mind for us lately is support for storage and stateful applications. It's a misconception about containers that they're only for these stateless applications. Traditionally, the work has followed the state. You put your services where your data is. Kubernetes enables it to turn around and have state follow work. In the cloud, you put your storage on a network disk and you just attach it to whatever machine you need. And you have equivalents on-premise as well. So now Kubernetes can provision storage dynamically so that pods can be created and given the storage that they need to persist longer than that particular process or that pod runs. Let's have a look at that. So our initial example, we said we have a pod. Again, it's a description of how we'll run a particular container in our cluster. It's the BusyBox container here. It doesn't do very much. But we're going to attach a disk to it. So we want a GCE persistent disk, a network volume, and we're going to take a disk with this name that's been created by somebody else, and we're going to mount that in that pod. So two problems here. First of all, the people who are running applications are not necessarily the storage administrators. They're not the people who should be creating storage. Secondly, if I took this config file and I wanted to run it on a different cloud, other clouds don't have GCE persistent disk. They have their own names for their own abstractions that do a very similar thing. So we can't decouple that from Google. We can't run this somewhere else. So of course, that's the first thing that we do. We introduced volumes as a first-class citizen in Kubernetes some number of releases ago. So there's providers for all the different types of storage you can imagine. So GCE, persistent disk, NFS, Amazon EBS, Ceph, Gluster, iSCSI, all the kind of storage volumes you might expect. Similar to the binding we did with the roles before, we connect a pod to its volume using a persistent volume claim. It's decoupled from the provider. So you create that thing with that name as the storage administrator of whichever particular platform you're on. And then you just say, call that, this pod uses a claim with that name. So now this manifest can be run on any of those environments as long as your storage administrator has created a claim with that name that you're able to refer to. That separation of concern means your ops team do the part that they're good at, the apps team do the part they need to do. Now, in cases where you just want to say, give me a certain amount of storage that has a certain class, this is where dynamic provisioning comes in. So you define in your claim, I want it to be a certain size, so 100 gigabytes. And you might say, well, I want it to be fast, which might mean backed by SSD. Or I might want it to be cheap, which might mean backed by hard drive. You just define what you want, and then in an environment where you have an API you can call to automatically provision storage, it is able to do that for you. You say, I want 100 gigs of fast disk. This claim will call out to that environment and then provision 100 gig of disk for you. And we have default storage classes in Kubernetes 1.6 for cloud vendors and also a couple of on-premise volumes. And this is cleaned up automatically. When you delete the pod that uses that claim, it will remove the storage, or you can have it persist longer if it's something you want to keep. It enables you to use stateful workloads. So we've talked a lot in the past about replication sets in Kubernetes, replica sets where you can stamp out the same thing over and again. If you're dealing with data applications, you want to say, this node has a third of the storage, and this node has a different third of the storage, and so on. And so these pods can provision the disk that they need to operate just on the set of the data that they run inside the database cluster. It's dynamic storage provisioning, and it's unique to Kubernetes. Now, the last set of features that I want to preview here are related to scheduling. It can be very powerful to provision a cluster if you want to do multiple availability zones. Declarative model says, I want to just run a container somewhere. Now, you might not really care if it runs in zone A or zone B or C because you want it to be redundant. But if you think about it, I'm going to say I'm running 3 replicas here. I really wouldn't like them all to land in zone A because there is a chance sometimes that a single zone will go offline. And that's very similar to, I used to have an email server and a file server, and they're sort of pets that I care about. We want to decentralize that. And we want to make sure that you still have the control to be able to define what you need when you need it. So let's talk about these failure domains. We have a cluster. We simply specify when we create the cluster that it wants to run in additional zones. So first up, with the gcloud command line there, we'll create a container engine cluster. It will spread its nodes evenly across the zones that you've specified here. So if we set a 3-node cluster, it will put 1 machine each in each of those zones. They are within the same region, so they have a fast, low latency interconnect, but they are on different failure domains so that they're operated on separately and they shouldn't fail at the same time. Now, by default, the scheduler will spread pods across all the nodes because, as we discussed, that's probably what we want. But let's think about a workload where we want to communicate with a service that's running outside of our cluster. In this case, we might have a service that's running in zone B in this case, so US Central 1B. Now, there is a small cost for communicating between zones, so we'd really prefer that the service that we provision inside our Kubernetes cluster also run in zone B. But in the case that zone B doesn't have any available space, we'd say, well, we'd really rather that it runs somewhere. We're going to prefer it runs in zone B, but we would accept it running somewhere else. Or we could make that a hard requirement if we wanted to. So this is the concept of node affinity. Here we have some additional YAML that we can add to our manifest for node affinity. So within this multi-zone cluster, or indeed any cluster where you might want to lock certain pods to run on certain nodes, you express that as a node affinity in the job spec. You have a key and a value and an operator. In this case, the key is the zone. So we say we want it to be in US Central 1B with that failure zone. Now, we still haven't said which machine we want to run on. We don't have to say it runs on the email server. It runs on this particular pet. If you have 5,000 nodes in that zone, it can pick any one of them, but it needs to be one that matches that rule. So what controls do we have here? Our affinity rule can either be a preference or a requirement. So in this last slide, we say required during scheduling, ignored during execution. So that could be preferred or required. But the ignored during execution means that if the labels on the node change while your application is running, so again, things won't move around in a cloud environment, but you could attach local storage, for example, then it won't change. But later on, we might have a thing which says required during scheduling, required during execution, in which case, if the node situation changes, then it would say, I'm no longer prepared to run this because it doesn't meet that rule. We have our operators, sort of in a group, does or doesn't exist, greater than or less than. And then we have the keys that it can check. Now, these are all just labels that are put on the nodes in your cluster. When you deploy in a cloud environment, you get automatically tagged with things like the zone and the region and the host name. Operating system and architecture, again, like AMD, 64, ARM. And then, again, in the cloud environment, does it have a local SSD? Is it preemptible? Which node pool is it in? These are all groupings of things you can say, I'm going to attach preemptible nodes, which might die, but run at a lot lower cost. And I could say, I would prefer my work run on these nodes, or I could say, I don't ever want my work to run on those nodes. And these are things you can do with node affinity. And the next new feature is interpod affinity. So in this case, let's assume we have a back-end service, and we say, well, we don't really care what zone that our front end runs in, as long as it runs in the same zone as the back end. This is called north-south communication, sort of up-down on the picture here. There are also cases for what we'd think of left to right, or east-west communication. So if we want 3 replicas of a service, we really don't want them all landing in zone A. That sort of defies the point. So we might set a require affinity to say that they'll land in different zones. Again, we'll look at the configuration. Very simple. We say that the app name we have specifying here to run the back end, and we want to require that to be scheduled in the place where the app name front end is running also, where the zone is that. And the topology key basically can say, put it in the same host, put it in the same zone, or put it in the same region. And as with affinity here, you can say anti-affinity and say, make sure you spread them out. They're not running in the same place. The last new mode is a little bit more complicated. It's called taints and tolerations. Now, this is like Affinity, but it's the other way around. So for Affinity, you say this pod would prefer to run here, or we're required to run it here. With taints, we say this node repels all pods. It does not want to run your workload. And then you can put exceptions on workloads called tolerations and say, I am prepared to tolerate to run on that particular node. So think of Affinity as being driven by pods, and taint being driven by nodes. Here's a good example of this. Let's say that in this particular cluster, we have 3 machines. One of the machines has 2 GPUs provisioned on it, but otherwise they're identical with 4 gigs of RAM. So if we have a pod come along and it says, I want to run on a node that has 4 gigabytes of RAM on it, any of these nodes fulfills the requirement to run that pod, so the scheduler could quite legitimately bind it to any one of those nodes. And it might say, OK, we'll go ABC, ABC, we'll run it and we'll go on node 1. So next up, we say, OK, now I want to run a pod that also needs 4 gigs of RAM, but it wants to use 2 GPUs. There is no machine left that has space to run this particular pod, simply based on the order at which they came in. That's not good. So if we'd put that first pod somewhere else, then we wouldn't be wasting those GPUs sitting doing nothing. So let's rewind and set this up a bit better. So we're going to set the flag on the node, which is the taint. We say it's tainted with a GPU label, so only a workload with a matching toleration will be prepared to run on that node. Now again, as with most things in Kubernetes, these are just key value pairs. So very easy, you can set them whatever you like, or you can use what's built in. The first pod comes along, and it does not have a toleration that says run on the machine with the GPUs. So our scheduler will say, I'm not going to schedule you on that machine. It'll pick one of the other ones. And it gets assigned to, again, machine node 2 in this case. Pod comes along, it says, I do have a toleration that's prepared to run on a machine with GPU. I tolerate that taint. It is now able to be scheduled on the machine and able to use that resource effectively. And it gets scheduled. So the final solution is this. We have a pod. It would like to run. This particular case, the taint says prefer no schedule, not require. So we may end up wasting those GPUs, but only in the worst case scenario, because we're not requiring that we hold them. So only in the case where there's nowhere else that it can run will a machine run on that particular node if it doesn't want to use those GPUs. Other hardware uses for taints and tolerations, TPMs, or any sort of hardware that you have on a machine, you want to ensure that it's used by the pods underneath it. You can use this to define priority groups and say this particular group has priority over these machines, and I want to schedule their work there first, and maybe more powerful and more expensive machines. You have, again, different scheduling modes, so prefer no schedule or require no schedule. Same there, prefer not to execute. Again, will it evict something that's running there if the taints change? And you can define how long it's prepared to tolerate something in various circumstances. So if you have a hardware failure, you can have the node automatically be tainted to say, don't execute things, and then the scheduler will stop trying to assign work there. But each pod can say how long it's prepared to run on a node that has that. Now, a use case for this is if you have a network partition on-premise, and you have something that's a replica of a database, it has a lot of data, or it has a lot of cache that's generated itself, you want to make sure that it waits longer. You say, don't throw that all away and say, I'm going to reschedule somewhere. Just let's wait it out for 5 minutes. I know that there are other replicas here who can serve this. You can set different toleration times per pod, a concept we call forgiveness. So being able to decide how long a workload will wait somewhere before we schedule it somewhere else. Last new feature with schedulers is the ability to write and run custom schedulers. Now, a scheduler, all it is a loop that matches pods to nodes based on conditions. So with custom schedulers, we mark the pod as saying it's going to be scheduled by a particular scheduler with this name. The system scheduler sees that we've asked it to use a different scheduler, and it ignores it. It's not going to be put on a node, and it's not going to get to start working. How do we get it there? We write our own scheduler. Someone shout out a programming language. Sorry, Bash? Yeah, why not? No one actually did shout out Bash. But here's a scheduler showing you written in 15 lines of Bash. So it's a loop that looks for pods. Say, look for pods that are not bound. And then it just picks a random node in the cluster, and it creates a binding, again, an object that takes a pod and a node and binds them together and starts that workload running on that node. That's all Kubernetes really is. It's a way of saying, here's the things that I want, here's the state of my environment, and a sequence of controllers that are continuously watching to make sure that you have running the things that you have asked for. Talked a little bit about Container Engine earlier. Container Engine works on the idea that we have this fantastic site reliability engineering team looking after services at Google. Why aren't they looking after your services as well? So with GKE, Google manages your control plane. Once you click Create Cluster, we create a hosted master node. If you're familiar with Kubernetes, it is exactly the same code we run on GitHub. It's exactly the same components. You can take the same thing, but we just manage it as an API that we look after for you. So it's not about just deploying the cluster, it's about the management of it. It's making sure it's monitored, making sure that it's, the master state is backed up, that we restart things when there's a problem, we resize them, we upgrade. We're continually keeping up to date with the latest the Kubernetes version and with security patches on the operating system for the master. This is how we've been 99.5% SLA. We've now got the components we need on the nodes, so you don't need to worry about integrating your nodes with logging and monitoring, because when you provision nodes in GKE, they have an agent on them which automatically connects to output your logs to Stackdriver and automatically connects in with our monitoring service there. Connects in with our layer 7 load balancer with an ingress backend, and then it provides the runtime on the box so that you can say, I now want to run my pods and have them run. So all you need to do is give us the manifest files, the YAML files, to specify what you want to run. You don't need to worry about running any of this. We've now gone one step further, and we're letting Google SRE manage the nodes. So with Manage Node Upgrade, we can have our team upgrade the Kubernetes version on the nodes, upgrade the node operating system. This is something you just opt into. You say, my particular nodes, I want to allocate auto upgrade to them. It's free while it's in beta. We also have node repair, where if we notice that a node isn't working for some reason, let's say the disk might have filled up, or again, a network partition, it can automatically note and repair nodes. It can automatically stop traffic. It can cordon that node and stop pods being scheduled on it, drain the pods that are on there, assign them somewhere else, and then rebuild that node. All this is done with a full audit trail. It's very important to be able to tell what changes were made to your hosting environment and be able to tell what changes were done by people and what changes were done by the robots. Okay, so given the name of our conference today, I wanted to finish by telling you a little bit about what we have coming up next. We are already hard at work on Kubernetes 1.7. Today, I think we're at 1.7 Alpha 3. We're due out on June 28th. Again, these are sort of 3 months between releases and very good at hitting dates in that community. Some of the things we're working on at the moment, better support for GPUs. Again, in an on-premise environment, being able to tag nodes and say what they're running or attach them in a cloud. We're improving the efficiency and the secrecy of secrets. So you will have seen this morning's keynote talking about our key management service and being able to back-end the secret objects that have application configuration. We're looking at how we connect them up to our key management service and to open source systems like Vault from HashiCorp. We're having a contribution for a team working on internal load balancing using IPv virtual switch, which is faster than the IP tables implementation that we have. There are a lot of improvements around third-party extensibility. So the third-party resource and the aggregated API servers are ways of you being able to say, I'm building in functionality that extends the Kubernetes API and then publish it through the same API server to users inside your cluster. Looking at being able to do upgrades of nodes statefully, so we can upgrade the version and keep workloads running on there, for example. And something very interesting to me is the work we're doing around our service catalog and service mesh integrations. There's a presentation at the end of this month at GlueCon where we'll talk more about what we're doing to bring internal service meshes to Kubernetes. Now, all of this has got you inspired to get started with Kubernetes. There's 2 things that I recommend. On the left is Minikube. Minikube is a VM that you download and run on your machine, which has a Kubernetes environment that you can play with straight away. It's really just a single command to download. You connect to that. You can start deploying all of the configuration files that you see in the examples on the web. It's really easy to get started with Kubernetes. Once you decide you want to move up to running in more than one node, you want to see what it's like in a proper multi-node environment, our free trial lets you start up a container engine cluster. Probably won't let you pay for 5,000 nodes at once, but you can have a play with a few at least. We have a booth in the main hall where we're showing a Whack-A-Pod. We don't have the physical machine, so it's more like touch a pod gently on the touchscreen. But it gives you an idea of how Kubernetes resilience works and how it recreates things after the event of service failure. Mentioned the talk tomorrow about globally scalable services, and then also this afternoon at 2:30 p.m. where my colleague Nacho is giving a talk on how you can do continuous integration and continuous delivery on top of Kubernetes. So I do thoroughly recommend that. So thank you very much. That's our talk for today. Please do tweet me your questions. Come and see me afterwards. I'll be around the booth as well. So thank you very much for coming.